Hello and welcome to third lecture in 19th chapter of our comprehensive course on AI, ML and DS. We are at present doing basic statistics, which is just a revision of what we have done in earlier chapters, 5th chapter and many other chapters. But therefore we are going very quickly. So those who find this very quick, they please refer earlier chapters. All this discussion has been done very slowly and in much more thorough manner earlier. Okay, what is interquartile range? Then we have seen that when we plot the box plot, there is some minimum value, there is some maximum value. So we just now defined range, that range is the maximum value minus minimum value for any data set. So 12 minus 7 here, or here also 12 minus 7. And the coefficient of range is minimum minus maximum, maximum minus minimum and maximum plus minimum, right? So L minus S and L plus S. So here also I can define range is maximum minus minimum, so that is 70 minus 12. But that does not give clear idea that we have seen that this has also range 5 and this has also range 5. So if it is given to you that two data distributions are there and both have range 5, what can you say about them? Are they same? So you cannot give a guarantee, because here there was a uniform distribution, but here the distribution is highly skewed towards the higher value. That means more data points are found near the highest value and higher value, while less data point, only one data point is found at the minimum value, and there are no data points here somewhere. Okay, so that idea cannot be obtained, that what fraction of data points are in which region. So for that we have defined this interquartile range. Whenever minimum and maximum values for a data set are found for a sample, we can also find the median easily. We have seen how to find the median, and median is what? Median is that observation. So here suppose 45 is the median, then median is that observation. 50% of the observation are below it and 50% of the observation are above it. Okay, then there is some number here, this number, which is called first quartile, Q1. Okay, what is that number? It is that number. 25% of the observation are less than that and 75% of the observations are more than that. Then we find this number, that is Q3. Okay, and that is called 75th percentile. So what is that number? 75% of the observation are below it and 25% of the observation are above it, right? So in that case, here we find that interquartile range is this 57 minus 30, or that means it is 25% and this 25%. Okay, that includes total 50% of the observation. This red colored rectangular box, that is called interquartile range. Okay, so this is one important measure of central tendency, of dispersion from central tendency. So you can say that 50% of the data points are within this much distance from the median. That is the definition of interquartile range, that the region in which 50% of the data points of the total sample are included from the median on the either side of median, that region is called interquartile range. Now here also, just like in range alone is having some problems, so we defined coefficient of range, that range is larger minus smaller value, but coefficient of range is larger minus smaller divided by larger plus smaller. Similarly, interquartile range, which is also called QD, quartile distance, so that quartile distance is Q3 minus Q1. This is whole thing is Q3, starting measuring from, that means 0 is here at x minimum, then this distance is Q3, while this distance is Q1, right? So then this 57 is Q3, 30 is Q1, and therefore quartile distance QD is equal to 57 minus 30, 27. But I can find divided by 57 plus 30, so that is 27 divided by 87. That quantity is called coefficient of QD, or that means it is called coefficient of quartile distance. Okay, then this mean and average deviation we have done here, so I'm not repeating it. This, okay, and similarly next one is also done, that is variance is also done, and standard deviation is also done here. Okay, so it is just a repetition, but I prefer to give some diagrams like this so that it is easier to quickly revise this thing. Now we take one example of a data set and actually manually calculate it. But remember, I already said, and again I'm saying that we will not calculate manually like this. We have ready-made functions in NumPy library, in SciPy library, and today we will introduce one new library also, which is called stats model. So in that library, various statistical functions are there. So first we do manually. So suppose there are 10 observations which are like this. Okay, 15, 12, 18, 11, 7, some negative observations are also there, minus 3, minus 9, plus 9, 14, 30. So what is the mean? Then that is the sum of all these observations divided by number of observations. So if I do the sum of all observations, then sum comes out to be 87, and then divided by this equals should be, I think, minus 9, then plus 9. Okay, then this 14 also should be plus, unfortunately it is a pasted image, so I cannot change it here, but this is plus sign, here also is plus sign, and this here also equal to is also plus sign. Okay, so then sum of observations is 87 divided by 10, or that is 8.7. Now next I want to find that deviation, and for deviation I will take each observation minus the sample mean. So each observation 15 minus 8.7, 12 minus 8.7, 18 minus 8.7. But as I said, sometimes it may be positive, sometimes it may be negative. For example, here minus 3 minus 8.7, that would be negative. But that then positive values will cancel each other and it will give false idea that the deviation in the data is less. So we take absolute value. So absolute value of 15 minus 8.7, 6.3, and 12 minus 8.7, 3.3, 18 minus 8.7, 9.3, and so on. And then I find the sum of all these, that is called, and divide it by number of observations. So if I find the sum, it is 62.2, and divide it by number of observations, so that would be 6.22. That is called mean absolute deviation, MAD. Okay, then what is the variance for this data? So then I have to do this number only, but square it. So square of 6.3, square of 3.3, square of this, square of 2.3, and so on. Again, when you take square, even if you have not taken absolute value, still the square will automatically become positive. And then I do sum of all these squares. So sum of all these squares, suppose, comes out to be, you can try at your home, that it will be 642.01. Okay, so then divided by number of observation minus 1. Okay, that gives sample variance. So number of observation are 10, 10 minus 1, that is 9. So that sample variance is 642 divided by 9, or 71.33. Okay, and the standard deviation of the sample, that is square root of this 71.33, so that is around 8.446. That is the standard deviation of this data. If instead of sample, if you are asked that this is a population, which is unlikely, because a population is always a large data set from which a small sample is taken. But if this is a population, then while finding that variance, you will not divide by n minus 1, but you will divide by n only. So 642.01 sigma xi minus x bar whole square divided by n, 10. So that will be 64.202. That is what I was saying, that the sample variance gives reasonably good estimation of population variance, which you cannot calculate in practice, because here there were only 10 data points, but think about that 2 million data point example, then you cannot find population variance. But sample variance is fairly close enough, and standard deviation will be even close enough. Sample standard deviation, population standard deviation came out to be 8, and sample standard deviation came out to be this 8.446. Okay, so that means that sample standard deviation gives a fair estimation, reasonably accurate estimation of population standard deviation, right? But as I said, will we calculate this way by subtracting and taking absolute value, then finding the square, which will require a calculator also, and then finding the square root? No. We have ready-made functions. So first, let us create our data set, and then we will use that functions. Okay. So this much I am taking in next cell, just for the sake of clarity. Okay. And here first I will print my data frame. So df, and this kind of data frame is created. 10 observations from 0 to 9 index are there, and these are the values of the observation. Now I must find sample mean, sample that is variance, and standard deviation, and mean absolute difference also. So in that case, I can directly use this thing. Dot mean is the function. Similarly for median, dot median, and for mode, dot mode, and then it's a zero. Zeroth element, because if I will print that dot mode first, then you will realize why this 0 is coming. Okay. Similarly for variance also dot where, and for standard deviation also dot std. Dot you will apply to whom? Then to the data frame. So data frame dot mean, data frame dot median, data frame dot mode, data frame dot scores, and data frame dot score standard deviation. Correct. So that will give me this. Now let us first calculate that. And let me first only print that mode, okay, mode value, so that you understand what is the reason of including that 0. Okay, so here I think okay, let us see, it will not be 0, 90. Yeah, it is 90. This is no, yeah, it is 90, and this 90. So I think this 0 may, okay, let us see type of it, because sometimes mode should be a number. So let us see mode value, what is its type. No, it is also a number, numpy int 64. So then I think perhaps this 0 is not required. Okay, and if I write type of mode 0, then in fact it is giving invalid index to a scalar variable. Correct. And if I write the value of mode value 0, then that is also incorrect. So this is actually some kind of mistake only. So we will just write. So it is easier even than what I said, that there is nothing to remember, just data frame name and the corresponding function. If you are finding mean, then use mean. If you are finding median, then use median. If you are finding mode, then use mode. Variance, then variance, and standard deviation, then standard deviation, and print out. So you will directly get the output. And I think this is the same. No, this is not the same data set, but I could have taken the same data set, and that is 15, 12, 18. Let me even change here quickly. Okay, so 15, 12, 18, 11. So 12, 18, 11. Sorry. Then 7 minus 3 minus 9, 7, -3, -9, okay, then +9, then +14, then 13. Okay, and let us find the, now it is the same data frame as what I had done and we manually calculated. Now let us calculate by program and check our manual results. So mean was 8.7. Here also the mean was 8.7. Okay, the median is 11.5, which we did not find. We directly found the mean absolute difference, which was 62.5, which here is not found. Then mode is also not found. Variance was for sample 71.33. Here also you will get 71.33. So important thing to remember is this, that whenever you use this ready-made function variance, where it gives sample mean and not population mean. Okay, that means it includes the formula with n minus 1 in the denominator, that is sigma xi minus x bar whole square divided by n minus 1. Okay, and that is expected because you are not interested in population. You cannot take entire population. You can only take sample. Okay, so entire art of statistics is finding population matrix from the sample matrix. So your library should give sample matrix. The standard deviation is 8.44. Okay, 8.44, right? So this is the value. Here I will save these only because, okay, this is the explanation of the code. There is nothing much to explain here. And what is the application of this thing? So that part and this Chebyshev's theorem and this thing that we will do later on. Okay, that means in next lecture. So thank you, and we'll meet in the next lecture.